Good afternoon, and welcome to this webinar where we will present the results of the report on impacts of National Science Foundation engineering research support on society. I'm John Anderson, President of the National Academy of Engineering. Before we get started, I want to take a moment to introduce you to the role that the National Academy of Engineering plays in addressing the engineering challenges of today. The NAE is one of the three academies comprising the National Academies, the other two being the National Academy of Sciences and the National Academy of Medicine. Together, the three academies oversee the National Research Council, which executes, validates, and disseminates the technical and policy studies conducted by our organization. Since its inception in 1964, the NAE has been called upon to provide independent, objective, and evidence-based advice on issues involving engineering, technology, and innovation. As advisor to the nation, the NAE is able to convene the best and brightest minds in engineering and technology to respond to issues of importance in a timely manner, to provide objective, evidence-based studies and consensus reports, and to inform policy decisions that improve our nation and safeguard our citizens. This ability to convene the best engineers in the U.S. across all engineering disciplines to address some of society's toughest challenges makes the work of the NAE unique among other engineering organizations. The experts who participate in National Academy studies and advisory activities represent a broad mix of engineering disciplines and a cross-section of leaders in industry, academia, and government. This diversity of thought and know-how enables the NAE to accomplish its core mission as a trusted voice of engineering leadership. The report being presented today reflects the collaboration, research, and perspectives of a team of experts tasked with identifying some of the major impacts that engineering research has had on society. This research was made possible by funding from the National Science Foundation. This report is intended to draw attention to engineering's impacts on society, highlighting the stories of people who have benefited from NSF's supportive research and education, and who have brought about technological innovations as a result of their work. Indeed, what makes this report unique among the studies done by the National Academies is its focus on stories and people, rather than an analytical study of a topic. In short, we are presenting the human element of engineering and the role that federal research and education support has in enabling the transition from research to reality in ways that improve society and our daily lives. Think Google, 3D printing, and artificial intelligence, to name a few. David Butler, the study director, will now give us more details about the study. David is the J. Herbert Holloman Scholar at the NAE and director of the NAE's Cultural, Ethical, Social, and Environmental Responsibility in Engineering program. David, I turn the microphone over to you.
Thank you, John. I'm pleased to be able to speak with you today about this study. As John mentioned, I am a staff officer in the National Academy of Engineering and was the staff director of the study that we're going to be talking about today. This presentation is going to cover what the National Academy of Sciences and National Academy of Engineering are, how this study came to be and what the tasks were, the expert committee that was convened to conduct the study, and the content of the committee's report. And what I'm going to be doing is setting the stage for the presentations of Dr. Dan Arvizu and Dr. Nick Bennett, who will be addressing the two of the primary issues addressed in this study: engineering's impact on society and how to communicate them. National Academy of Sciences is not a part of the federal government. Instead, we were chartered by the Congress back during President Lincoln's administration as an independent, non-governmental source of advice to the federal government. The National Academy of Engineering, of which I'm a part, was founded in 1964 as a distinct entity within the National Academies with the mission to advance the welfare and prosperity of the nation by providing independent advice on engineering matters and promoting a vibrant profession and the public appreciation of engineering. Now, the particular study we're speaking of today came at the request of the National Science Foundation. The NSF is a government organization that funds scientific and engineering research and education. They provide funding to students, educators, and researchers, to schools, colleges, and universities, to private research institutions, and to academic institutions, along with those institutions' faculty. The NSF asked that we help them in their efforts to bring a greater understanding of engineering's impact on society. In order to carry this out, National Academies formed an expert committee, and it had a few tasks that it was tasked with. Primary among these was to identify 10 extraordinary engineering impacts made possible from NSF investments. Now, those impacts might take one of any number of forms, including expanded technological and social capabilities, scientific breakthroughs, economic improvements, improvements in individual quality of life or national security, population health, infrastructure, or any number of other impacts. To accomplish this, we were asked to also organize a virtual public symposium, one that would highlight the information on impacts in society and would gather information for the committee's consideration. That was carried out in 2022 and resulted in the extraordinary engineering impacts on society proceedings that you're seeing here. That proceedings can be downloaded from the National Academies Press without cost. Our website also includes videos of the presentations that took place at that symposium. Another task we were given was to develop clear and compelling narratives for public engagement on the engineering impacts and provide guidance on how to reach and engage diverse audiences in those impacts. The work of this study was conducted by an expert committee, the members of which you see here. They include people who were experts in various of the engineering disciplines, people who formerly held senior positions within the NSF, and people who are experts in communicating complex technical and scientific information to audiences. We are pleased that all of them could participate and thank them for their work. The report that committee generated not only addressed the topics that we're talking about here, but also goes into greater detail on NSF's support of engineering-related research and education, and in more detail of some previous efforts to recognize engineering impacts on society brought about by NSF investments. The committee's report, the cover of which I've shown here, is our topic today. And with that, I am pleased to introduce Dr. Dan Arvizu. Dr. Arvizu was formerly the president and chancellor of the New Mexico State University System. Dan?
Thank you, John. And thank you, David. Appreciate those introductions. And let me start as I start to share my screen here. Let me start by doing a shout out to both the expert staff that Dr. Butler commands and David's work himself, as well as the committee, which you've now seen as being extremely important in this work. So without further ado, let me do this. We only have a limited amount of time, so I'm going to start with two things that I'll do here today. The first of those is I'm going to talk about after we heard the committee charge from the National Science Foundation and the Academy, we took to developing the framework for how we would respond to those committee charges. And so I'll talk a little bit about that framework now. The second thing I'll do is go through and do a pretty quick top-level synopsis of all of the 10 exemplary outcomes that we have highlighted. So let me get on with the framing of this particular task and project. Identifying 10 extraordinary engineering impacts made possible by and as David has already suggested, we were looking at these things from the perspective of very wide, broad understanding of whether it be technical, social, scientific breakthroughs, economic opportunity, individual quality of life, national security, health, and the things that you see on this slide. And we were informed, obviously, by the guidance that we were provided both by the Foundation and the Academy. We decided that we couldn't and wouldn't actually single out a top 10 set of achievements. They're in quotes. Primarily, that's been done on numerous occasions. And in fact, in our report, we talk about all of those that have done, the Nifty 50 at the 50-year anniversary, all the way through the number of other assessments that many folks have done, talking about great engineering achievements and impacts that have affected society. And so our attempt was not to necessarily try to define the best, but in fact, to define instead exemplars. And this is really where I think the committee spent most of its time, is understanding how to select a group of 10 exemplars, if you will, where the impact is very, very clear. And through the guidance that we have, obviously, in the time frame that the NSF in also various types of engineering disciplines, all kinds, including all the new ones, the bioengineering kinds of things that bring together interdisciplinary activities. The form of the impact, whether it's economic, social, or technological, and the nature of the support, whether it be for educational careers, individuals, institutions, and the quality of research, and all of those things were all part of how we decided to frame. One additional thing was that, as was made clear both by John Anderson and David Butler, that we engage young people, the next generation of those who would aspire to the engineering profession. And in doing so, to choose those in a way that could provide inspiration and motivation to the next generation across all various parts of our society and the richness of the diversity that we enjoy. So it was in that context that we started looking for how can we find people that can ultimately describe extraordinary achievements. They happen to be there, and when the young people see them, they can see someone that looks like them actually doing some extraordinary things. So this was what we were intending to do with this report. And the text is really to enhance the narrative, not necessarily to go back into a deep dive and talk, the historical evolution, although there is plenty of that kind of information in our report. So the 10 exemplars that we chose to highlight are given here, not in any particular priority order, but everything from additive manufacturing and specifically around 3D printing and the things that went with it, artificial intelligence since the beginning and all of the things that have evolved since then, biomedical engineering, and we'll focus on rehabilitative engineering, cybersecurity, something that NSF and DoD have been involved in for many, many years. And we took a little bit of a different departure on looking at outcomes that might not be totally people related, but maybe initiative or program related, in this case, engineering education and early career support for young professionals, something of great value to the profession and having many ways in which that provides impact. And we decided to highlight that. Material science and engineering and early centers and material science centers that were part of NSF. And again, in the next one with the National Science Foundation Engineering and Research Centers, the ERCs, we call them, were extremely important also in the development of the engineering impacts, I think, that have really benefited society. Likewise, things around the internet early on, we'll talk about that, and semiconductors and integrated facilities. Okay, let me get on to identifying those after I make the last statement. And in the graphics and in the following slides that you will hear, we'll try to talk about a little bit about what was the technology, what was the advancement that we're referring to, and then spend a little bit of time historically, how did NSF contribute and what kind of a way in which they participated. Talk a little bit about some examples of those outcomes and how they've affected society. And then ultimately look at it through the lens of someone who was there and provide that as a narrative to help, again, inspire the next generation. So with the limited amount of time, I only have 2 slides on each of the 10 different exemplars, maybe 3 on one of those. But the idea here is to whet your appetite. So in the report, there's multiple people, multiple highlighted things. I'll just due to time, I just have the opportunity to say a few things about a few of these before I turn it over to Dr. Bennett, who'll talk about communication. So additive manufacturing. I don't need to tee too many of these things up. People understand additive manufacturing. This is the opportunity that we get when we actually get those printers that actually can print according to some pattern and lay a material down in a 3D manner. And this has transformed traditional manufacturing in so many different ways. Different kinds of materials, design flexibility, accelerated production. Some of our colleagues in the national labs have actually 3D printed automobiles, they printed houses. These are ubiquitous, and there's so many different ways in which today they are important. The Strategic Manufacturing Initiative that NSF really launched in the 80s and 90s really engaged this technology, this methodology, and provided over 600 awards. One noteworthy person that was a part of that whole process was Ailey Sachs, one of the pioneers of the binder jet technology. This gave rise to literally being able to put a binding agent onto powders that ultimately provided opportunity for metal casting and metal parts that ultimately rivaled all kind of traditionally methodologies for metal. Dr. Sachs was an MIT faculty in the 1980s and really was one of the pioneers. Ultimately, Desktop Metal, a company that he and his colleagues founded, is now a very, very vibrant company with almost $2 billion in value and over 6,000 customers and 650 patents. So very, very instrumental in the additive manufacturing arena. And again, lots and lots of other ways in which NSF has contributed. Artificial intelligence, another area. We hear a lot about that today. And whether we started with Siri, remember that, and Alexa. Now we have ChatGPT and Claude and a few others. This is they are providing us and a service to society in ways that we could only imagine when these technologies were first introduced. In 2024, the analysis that's been done by our committee showed that almost 8 billion AI-related grants have been made by NSF, multiple universities, and many of them with substantial backing in the $10 and $20 million range. Absolutely incredible work that's been done for many decades, actually, in moving forward the technology. One example that's particularly noteworthy is Fei Li, one of the people that it many times is highlighted. We talked about artificial intelligence, and she was the recipient of an NSF Career Award, which let her and her colleagues at I think in her work continue to do some extraordinary things relative to large scale visual recognition challenges. The have to do with image recognition, recommender algorithms, speech recognition and facial recognition, machine learning and robotics we've talked about for some time. And in the case of Dr. Lee's work, she was very good in the image recognition part of that work. She started with a database that was relatively modest, and grew it to one that essentially had millions and millions of images, and the classification accuracy improved from less than 72% to greater than 97%, which is pretty amazing. Gaming industry was a big part of that, but a lot of work sponsored in the artificial intelligence arena. Likewise, I'm checking my time here. We'd had medical and rehab. There was sponsored in partnership with the NIH, the Veterans Association, and also the Department of Defense. And those partnerships have been going on for decades, 60 years in many cases, focused on biophotonics, biosensing, cellular and chemical engineering. And one particular tool that I think has really caught on is the so-called bionic eye, developed with biomimicry, microelectronic systems engineering at the University of Southern California. And that work is amazing. It's implantable devices that can restore some vision and perception of light and motion. And the photosensitive arrays send signals to the nerve cells to provide that signal to the brain. Absolutely amazing stuff. Lots of opportunity and space going in the future. Additionally, we've kind of focused on Rory Cooper's work at the University of Pittsburgh. Rory Cooper is a U.S. Army veteran. His military service resulted in a major spinal cord injury, and he's been active in his work and his science and research on a variety of things that help our wounded warriors, and specifically this particular project is one with a waterproof wheelchair, which I thought was particularly interesting, and it just expands the possibilities for all people that have similar kinds of injuries. Cybersecurity, another area of great interest and importance. The information age has ushered in an era marked by unprecedented connectivity and interdependence, and obviously bad actors have been there for a long time. Since the 1990s, NSF has been working on programs such as secure and trustworthy cyberspace, program, the SATC, and its predecessors, and have been developing all kinds of technologies. And it's really trying to understand how do we develop trustworthy infrastructures. That's been NSF's focus. And it is important because so much of the work that we do is specifically focused on maintaining security and privacy and those things that go with it. The work we choose to highlight here is since the early 2000s with some work that Lori Faith Craner, Dr. Craner, did at Carnegie Mellon. And she worked on a variety of things that are secondhand to us today. We see them all the time, and that is how do you update and otherwise provide safe passwords? None of us, I think, and Dr. Trainer's work early on set the ground rules, set the design parameters for how those things would be viewed. And NSF has supported that work for many, many years to provide us, again, the safety and security that we need in cybersecurity. I think it's important to note that one of the things that we committee thought very highly of was the fact that there are important things that don't really, aren't so much grant related as they are programs that help shape the future of engineering. And one of those, of course, engineering and a variety of the programs that NSF sponsors that relate to that. Broadening participation is a primary example of the merit review process, looking at how do we make sure that we are inclusive in the way in which we pull together activities that relate to scientific and education and research. In that context, several programs that come to mind. Advance was there to help our women better able to advance within the profession. 20 years of work with $365 million of investment in the advanced program. And 40 years ago, we had 6% women in the engineering profession. Today, we still are needing to do more progress, but we got greater than 16%. And in some of our engineering professions, such as chemical engineering, we're above 36% women participation in the workplace. Mechanical engineering and electrical engineering still a little lagging behind in the 14 to 16% range. But these programs have been tremendous in aiding, I think, professionals to get more involved and to help again the underrepresented meet better progress in that profession. Includes is another area where I think we're looking at underrepresented people in the entire area of engineering. The program we chose to highlight a little bit is one that was focused by Dr. Sarah Eichelhawk, a citizen of the Pawnee Nation and chief executive of the American Indian Science and Engineering Society, and she has been a stalwart proponent and key person in the ACES includes grants which supported those, and continued to really, I think, make an impression and a dent in our Native American communities across the country. Those numbers are still pretty dismal. The population, the indigenous population in the U.S. is roughly a little bit less than 3%, and we're still less than 0.5% of people in the profession. So we've got work to do here. But again, what the NSF has been doing phenomenal in terms of improving the impact to society that works. Materials material science and engineering is also another really important area. We started with a lot of the things that we do obviously relates to materials, so it's kind of ubiquitous everywhere. But ARPA, the Defense Programs, the Advanced Research Projects Administration, started an interdisciplinary laboratory program. ARPA, you've heard about it. We've tried to emulate that in other agencies now. And NSF actually had something that was very similar to that, and it was actually a successor to the ARPA interdisciplinary laboratory called Materials Research Science and Laboratories, and later the Materials Research Science and Engineering programs. A lot of work in that area, and tremendous work that focused on all kinds of things for sustainable biotech, textiles, biocompatible medical implants, and things as important in our transportation sector as the recycling of lithium-ion batteries for electric vehicles. Really important in all of these particular areas. I've got a couple of examples on this one because there's just so much to say about that. And in the field of nanoscience, one of the highlights that we use in the report is Dr. Mildred Dresselhaus, who many of you know as the Queen of Carbon, I think is what we would call her in our report. She had a number of mentees. She's clearly the most important person, I think, in carbon nanotube science over a long period of time. And she spawned a group of a number of different researchers, one of which was Baratunde Kola, who won the Alan T. Waterman Award at the National Science Foundation a few years back, and has been an incredible amount of work at Georgia Tech, and in fact, I think it's important that the designing of thermal transport things leading to, I think, startups, and in this case, a fairly significant company, Carbice Corporation, which is really focused on thermal management for all kinds of electronics and especially applications in space. Very important. Another person that I wanted to highlight also in here is someone that really, I think, are inspired by, and that's Dr. Paula Hammond, who's done some incredibly important work, specifically around thin films on polyelectrolytes. At the nanoscale level, she's able to deposit films that are so thin and so possible that so flexible that you can surround drugs and drug therapy of all kinds in a thing that looks a lot like shrink wrap, and then strategically place that near where there might be a tumor for cancer or whatever, and it provided for precision control and in fact has been revolutionary. Dr. Hammond is one of those incredible individuals, only a few of which has been able to be elected to the National Academy of Science, National Academy of Engineering, and National Academy of Medicine, all three of those academies for tremendous work that she has done. Again, all of that sponsored early on by the National Science Foundation. As I move on, I think the research centers, much like the material research centers, have also been important areas of our development, you know, at NSF. And there were overall, I think, a total of 9 ERCs that have been sponsored as of 2023. 25,000 peer-reviewed papers, 800 patents, 1,300 licenses, 2,500 invention disclosures, 240 spin-off companies, and conferred more than 14,400 bachelor's, master's, and doctoral degrees to ERC students. So tremendous work going on in our Engineering Research Center, interdisciplinary, solving big complex problems with multiple institutions, a tremendous new approach, I think, to the way in which things have gone. One highlight is Dr. Karen Lozano, who's at University of Texas, Rio Grande Valley, a minority serving institution, 90% Hispanic. And Dr. Lozano has done tremendous work in taking those material research center attributes and in exposing, you know, a group of underrepresented students that have never had that opportunity in ways that have been revolutionary. And interesting enough, Dr. Lozano was recently elected in the National Academies of Engineering as well. Internet advances. I think Dr. Anderson at the very beginning of this talked about Google. You know, we have a tremendous amount of NSF support for all things that have related to the internet and the evolution of the internet over time. Everything from, you know, ARPANET to NSFNet to all those things that ultimately have led to who we are today in terms of information. And early on, that transmission control protocol and the internet protocol. We hear about IP addresses all the time. This is what that means. And Mosaic, which was one of the first, you know, freely available web browsers that really were a big part of that. The thing we're highlighting today is Dr. Susan Estrada in 1986. She was a part of trying to introduce, if you will, the topic of the internet to K through 12 teachers on the web, and formed a publication called Captain Internet. And ultimately, as that particular thing got more and more traction, it was actually credited by the originators of actually the expression that we all talk about, surfing the net. Well, this is where that comes from. And I thought that was kind of cool that back in, you know, in the mid 80s is when all that kind of stuff really happened. Okay, I'm almost done here. I've got 2 more to go. The semiconductors and integrated circuits. We all know that the brains behind all of our high-tech electronics is in the chips. Semiconductors and integrated circuits. This started back in the 1950s, you know, with Bell Labs, and then ultimately it transferred over to start with improvement of semiconductors and Moore's law, and the number of transistors on a chip have increased, you know, exponentially. There used to be tens of those on a chip. Now there's billions and billions of those on a chip. It's amazing how that has worked. It's such an important part of our overall fundamental idea about how we actually use technology to help society, and it helps all these various things. So semiconductors have become indispensable in our modern lives, and the Chips and Science Act that was signed and passed in 22 dedicated a lot of money to help create the infrastructure in the U.S. for our chips and manufacturing that go with it. We still need the appropriations to go with that. There was a little bit of supplemental, but there needs to be a lot more, just FYI. But important, National Science Foundation has made a tremendous amount of activity and impacts as a result of the things that they've sponsored. One particular you know, thing that we'll highlight is Dr. Sujay King Liu. who's comes from parents that immigrated from Taiwan, made significant contributions at Berkeley through an NSF faculty grant, and in fact has continued to do great work in her Center for Engineering Efficient and Electronics in Science, and she's been credited with pioneering work on crystalline silicon germanium, as well as co-inventing the 3D thin field effect transistor. So some incredible activity by some incredible individuals that have really changed the world as we know it today. Now, another topic of great interest to me personally, the renewable energy. NSF has been a big part of renewable energy across all of the various technologies, solar, wind, biofuels, efficiency, all of those things. Where most of the work, I think, that has been sponsored in renewables happens within the Department of Energy and its national labs. And one of the national labs I used to run, the National Renewable Energy Laboratory. There's been some great and tremendous work happening at NSF, both fundamental and applied in so many different ways. That we highlight in this case some of the centers. NSF funded a University Cooperative Research Center for Wind Science and Technology at the University of Massachusetts Lowell and University of Texas Dallas. Lots of work going on in all of those areas. Again, many grants for individual PIs. One that I particularly like is work that's been done by Dr. John DeBerry, MacArthur Genius recipient, someone who's done exceptional work, and John did his work on addressing fluid transport and flow dynamics in aquatic locomotion. What's interesting about this is the way he looked at the way in which fish school and the way in which they interact with one another, and was able to deduce, I think, important engineering approaches to improving the energy production in a footprint of land that has wind turbines on it by looking at the interaction between the wind turbines and optimizing that in ways in which mimics the biology of fish schooling, which I thought was fascinating. And in fact, great work that Dr. DeBerry has done, I think, promoting that. So in conclusion here, I wanted just to say the investments that the National Science Foundation have made in engineering, education, and research have played really a catalytic role. There's no question in our minds about that in advancing science, technology, and engineering. The interdisciplinary and intersectoral collaboration has been something of an important, I think, emphasis that NSF has made. Especially as it relates to centers and the interdisciplinary work and the work with other agencies. And it's provided positive impacts to society, building on things that other agencies have started or in complementary ways that the other agencies have done. And then, of course, NSF's investment, both in women and underrepresented, students who are aspiring for work in the science and technology professions, and specifically engineering. I think NSF continues to do a tremendous job, have already done and continue to do a tremendous job in promoting the science and promoting the profession in a way that can continue to have great impacts on our public society. So with that, I think I will like to introduce Dr. Nick Bennett, who will be addressing our work on the other two items that we had as our primary task: developing clear, compelling narratives for public engagement and providing guidance on how to reach and engage diverse audiences, both of which are important. We've hopefully gotten the ingredients of those teed up in the report. Many individuals have been highlighted, and this would be a time to maybe turn those into some compelling stories. So I'll turn it over to Dr. Bennett.
Thank you, Dan. Yeah, y'all certainly made it easy for us to put together some materials on these amazing advancements. All right. So you have gotten to hear about the National Academy of Engineering's report, highlighting all the positive impacts from the National Science Foundation's support of fundamental engineering. So I teamed up with the Alan Alda Center for Communicating Science, as well as MIT, and our job was to create some example communication materials to highlight these amazing impacts. And so we developed 5 pieces of content, ranging from everything from articles on Dr. Arlene Simon to interactive comics about the Queen of Carbon and her mentors and all the people that she inspired, as well as video reels on the amazing pieces of technology that are in our lives, as well as earthquake shake tables. This content was developed by undergraduate students in journalism and mass communication at Stony Brook. I served as kind of the project manager as well as the expert in communication. So I brought in the research, made sure that we were using best practices in communication, and the students developed the materials. Very importantly, because we were aiming many of these materials at younger audiences, we also had high schoolers from Dr. Ebony Hearn's MIT group of scholars to give us feedback and tell us which pieces were engaging, how they could be improved, and how we could actually target them to that specific group. Like I said, we have 5 examples. You can check them out on the website. Today, we will have time to look at one of these examples, and I'll give you a quick peek behind the scenes about how we made these. And so we're going to take a look at one example that we developed to showcase some of the National Science Foundation's innovations behind the innovations.
Everyone knows how dangerous earthquakes can be. Engineers want to design buildings so they can be safer. So they test out their designs. They can use computer simulations, but the designs need to be tested in the real world as well. We had a limited budget, so we had to cut a few corners here and there. Luckily, the National Science Foundation supports the innovations behind the innovations, so they can fund projects like the largest height-capacity 3D shake table. With this table, engineers can recreate realistic earthquake conditions, so they can make older buildings stronger and set safer design standards for new buildings. Everyone knows.
So this piece that you saw, this very quick video, is aimed at about teens and maybe a little bit older, especially those who live in areas of the United States that are vulnerable to earthquakes. And so when we design a piece of communication like this, we want to make sure we have an objective in mind. And so for this one, we had multiple, but one of the main ones, hopefully it gets across, is to make visible some of these innovations behind the innovation. So this funding from National Science Foundation makes so much possible. And there's so many impacts that we were seeing from Dan's presentation that are in our daily lives. And so the great thing about arts and communication is that they can make these visible. We also, another thing that came up in Dan's presentation that feels very relevant to this one as well is this awe, thinking about and learning about this earthquake shake table and the amazing things that we've been able to accomplish. There's just a cool factor to the US's largest shake table. And so part of our goal here was also to inspire some of that awe. And then a third goal we had was to frame engineering as really important and relevant to disaster and hazard mitigation. And so this content's meant for a general audience, a wider audience than those of us who are already geeking out about engineering. And communication theory tells us that those of us who are already interested and motivated, we don't really need a lot of convincing to read a lot of articles about this. We're already fine doing what we would say high cognitive effort. So we don't mind doing a little bit of work. But for those who are not yet interested or motivated, we want to make sure we are drawing folks in, sparking their interest, providing what we would call heuristic cues. And so in this case, it's really important to remember the importance of making the material fun. We want to make it engaging. We want to spark interest. We want to invite people in to be curious. There's not a ton of information in this video, but hopefully it sparks enough interest that someone might then be interested and motivated and want to learn more. And if we look at studies of the most popular videos online, like on TikTok, this genre has a wealth of like amazing physics and chemistry experiments. The most successful ones online show what we call procedural science. So getting to see entertaining experiments, getting to see the process. So we thought that highlighting the process of engineering, how engineers actually test buildings, would be very aligned with that best practices. This is really important on social media platforms, which algorithms have a lot of downsides, but one of the pluses is that you can reach an audience you wouldn't normally reach. And much of our social media audience is younger, is female identifying, and those are the same audiences, as Dan was saying, that engineering is most interested in reaching out to. So this quick video used to explain the procedure of engineering and a really cool piece of engineering infrastructure is really aligned with best practices, other than being very fun to make. And so length is important. Videos are great for communicating science, but the research says if they're too long, they actually score about the same as like a boring PowerPoint. So if you want the audience to pay attention, to be engaged, short is better. So it was a big struggle for us not to try to fit every single thing in. As Dan said, there's so many amazing innovations. We just needed to make it short and sweet. And we also were really careful about making this a narrative. Dan was really emphasizing the people and the stories earlier, and that's also aligned with communication best practices. So the best practices says, instead of having a very formal expert, if you have a narrative style that's more explanatory, even animated videos, folks remember that content even better. Unfortunately, most of our materials that come out of our universities, our research institutions, we do tend to be quite formal. So this is maybe an invitation to think about more informal styles, using more humor, being more personal, bringing yourself into it. That can actually be very good for communicating engineering. And so for this reason, we advocate this sort of style if you are trying to reach this particular audience. And this content is very interested in spurring interest, curiosity, wonder, awe. And I mean, to be honest, we had material that was very easy to do that with. It already is very, very cool. And there's a variety of types of awe that we can communicate. But the way that it works psychologically is when an audience encounters something vast that affects them emotionally and motivates their curiosity. At the same time, the research on awe tells us, and wonder tells us to be careful about burning people out on just always sparking curiosity and always inspiring wonder. So there's another great reason to make this video short and sweet. And with such a short video, it's also really important to be intentional about narrative design. So if you looked at all of the drafts that we had big, long lists of bullet points about all of the amazing research we had done, all of the communication we had done with the center that was behind this, all of the amazing research that had come out of it. There was so much we could have said. And what it looked like at first was kind of a bulleted list. And what we had to do was turn that into a main topic that we could tell a story about. So this kind of, and then bringing in humor, personality, informal language. Research tells us that's actually better for the particular audience that we were trying to reach. That's normally not reached by engineering materials that have kind of more formal feel. And so with that, I also want to zoom out and talk about some of the research my colleagues, John Besley and Anthony Dudo, do. So when we think about a particular video like this, it's what we would call a tactic. But when we think about longer term communication strategies, we really want to think, again, long term. We want to think about our long-term goals. What are our short-term objectives we want? And then we want to pick tactics. So in lessons learned from these examples, I want us to remember that these are single examples and that they would be a part of a larger strategy. So first we would pick our goals, and then we would think about the objectives, and then we would say, all right, we have a bunny earthquake shake table video there. And then also remembering that good communication materials take time. So this was a long-term collaborative effort between myself and many students. It's really important for it to not to be an add-on at the end. And we also want to think about communication is this kind of external piece that we are showing and signaling who belongs in engineering. And so telling stories, showing the human side, this can all do a great job of doing that. And while we're doing that, we also want to think about designing our engineering spaces for belonging so that when folks are invited in, they're invited into a welcoming space. With that, I have so many people to thank and one animal. The peer earthquake shaking table team was very generous with sharing their materials and letting us make bunny videos about their earthquake shake table. Gary May, Arlene Simon were very generous with offering interviews to the students. We had students at Stony Brook, Lori Saxena, Naya Priestley, and at the Alda Center, we had Laura Lindenfield, Elise Wallace, Lori Key. At MIT, Ebony Hearn and her high school scholars helped us out. Mark Major, my spouse, came in and did some voice work for us that you heard, and also some of the editing. And of course, Ampersand the bunny for his amazing acting skills. And thank you for being here. And now I'll send you back to David for details on where to download the report and the supporting materials we have presented today. Thank you so much.
Thanks very much, Nick. And thank you again to Dan Arvizu and to John Anderson for their presentations. We've just scratched the surface of this very long and detailed report. But what we would very much like to do is share the entire report with you, and that is something that we can do without cost through the National Academies Press. They have posted this report to their website, and you could see here the URL for accessing the report. You could also simply go to the National Academies Press website and type in keywords like impacts of the National Science Foundation in order to find this report. We have a number of other resources for this report, which we've also posted to the website of this study. In addition to this, we've set up a QR code that if you want to use your phone, you can click directly onto the report. We hope that we've given you the opportunity to learn a little bit about engineering impacts on society, about how to communicate them to the public, and about the exciting work that engineers do every day to affect society and to address some of its biggest challenges. We thank you very much for your attention today, and hope that you found this presentation to be helpful. Thank you again, and good afternoon.